Hello, this is my lab report for lab 3 for a black hole. So the problem we're trying to solve is part 1. We're trying to find the mass of a black hole by analyzing the motion of a star moving around that black hole. Part 2, we're going to try to fly a spaceship with an initial velocity that escapes a planet's orbit around the black hole and actually comes near the black hole. And then also we'll try to get the spaceship to leave the planet and orbit the black hole. And all three of these parts come down to these fundamental principles: Newton's second law and the gravitational force, as shown by these equations. So for the organization part, we'll go through a part 1 glow scope overview. We'll run the code visualization and discuss the what does it mean question. Then we'll do the part 2 glow scope overview, run the code visualization, and then we'll try the what if question with edits to the part 2 code to make the spaceship orbit. So part 1, we know our star's position and velocity as shown by this while loop here, given the random seed that gave us the position, and we can get the velocity by doing just delta x over delta t and delta y over delta t as shown here. And then we can get our v initial, v final, as well as our momentum initial and our momentum final, because we know the star's mass, because we know that momentum is equal to mass times velocity right here. And we can get our dp dt, our rate of change of momentum, by dividing by delta t from delta p. And this is of course equal to the net force, which is Newton's second law. And then we see the parallel component can be calculated using this formula. And we can see it is equal to dp dt, but specifically it's actually equal to this. And then we did that same exact calculation right here with our unit vector and our d mag PET. And then we get our dp dt parallel. And then we get the perpendicular component by subtracting dp dt parallel from the total dp dt, because those two added together will equal dp dt in the end. And then in order to find the mass of the black hole, we use the gravitational force formula to get the mass by setting the equation equal to the mass of the black hole. So originally it was like this, and imagine that this big M is the mass of the black hole. We simply times by r squared divided by r hat, and then we divided by g times the star's mass, and then we can get the mass of our black hole. And if we run the program, we can clearly see that this is printing out the masses, and the average is approximately 2.15 times 10 to the 34th kilograms. Now we can do the what does it mean question, which is essentially asking us what is the difference between the rate of change in momentum and the net force. Well, the rate of change in momentum is delta p over delta t, which is mathematically equivalent to the net force, which is of course Newton's second law, but these are still not the same, even if they're mathematically equivalent, where the rate of change in momentum is the analysis of the system's motion, while the net force is the interactions on the system that causes the rate of change of momentum of the system. So the net force acts on the system, and the system then has a rate of change in momentum because of that net force. So now we look at part 2, we can see that we plugged in the mass of the black hole from part 1 right here. And to calculate the net force on the planet and the ship, we had to use gravitation again, as seen right here. We can see the big G, and then we can see the same calculations for all of these. And then we add the gravitational forces from the two sources. For example, for the net force on the planet, we need the force from the ship and the black hole both on the planet. And then we have to, of course, we update the planet's velocity and position, as well as the spaceship's velocity and position. And we use the forces calculated before, of course, to use that, because this is to be the velocity update formula, which requires an F net. So the F net on the planet, which we calculated right here, and then the F net on the spaceship, which we calculated here, will have to be used. And then we use the position update formula to update the ship's position. Now we'll run it, and we can see that the spaceship does come close to the black hole. So what if? Let's try to make the spaceship orbit around the black hole. So my thought process personally was to try to get a close orbit is too hard, where if you look here, trying to get to orbit in that tiny little circle around it is far too hard, because the initial velocity is simply too high, where it will curve around but there will be no orbit. So the best choice is to make the spaceship's velocity close to the planet's velocity. So I attempted this here. So it's enough so that it still escapes the planet, but it orbits around the black hole in a similar trajectory as the planet. So let's run it. Now you can see that it is very close, and actually it's going to take a little while. So I'll just let it run on the right side here. And this is the ultimate result that we're going to get, which is obviously pretty close. And then we can see that it's super close, but not perfect, as the spaceship has to stay ahead of the planet to escape the planet's pull while still retaining this orbit around the black hole, as you can see as it's moving right here. Thank you.